Welcome to In the Mix, the show that puts masonry in the spotlight, block by block, brick by brick. I'm your host, Adam Hutchinson, Executive Director, Professional Engineer, Industry Advocate, and believer in the power of resilient building design. Every week, I sit down with architects, engineers, contractors, and building owners to break down how masonry makes our communities stronger, safer, and more resilient. We're here to share stories, tackle the tough questions, and help you see what's possible when we build better together. Let's get in the mix. On today's episode of In the Mix, I sit down with Alex Watchman of Clark Barnes to talk about a pretty innovative approach to mid-rise multifamily construction, combining both CMU and mass timber into one integrated structural system. What started as a conversation at a Mariners game turned into a much deeper discussion about how concrete masonry and cross-laminated timber, or CLT, can work together to create buildings that are faster to build, more resilient, and potentially more cost-effective. Alex breaks down the thinking behind their proposed wood and block system, how Type 4C construction is creating new opportunities in multifamily housing, and why this hybrid approach could help both the masonry and mass timber industries grow together instead of competing against one another. We get into the real-world side of this: building codes, seismic design, fire ratings, construction sequencing, scheduling efficiencies, and why this approach may be one of the smartest ways to maximize the 85-foot height limit without triggering high-rise requirements. Now, let's get in the mix. Today we have Alex Watchman from Clark Barnes on the In the Mix podcast. Alex is a licensed architect in Washington, graduate from University of Minnesota.
Yep. And
then a graduate from a graduate class at Harvard. So today the whole point is to talk about what your CMU checkoff grant request is about, why it's important to look at how CMU and CLT can work together as a symbiotic relationship for multifamily housing to help grow the CMU market and get CLT accepted a little bit more too.
Yeah, I'm excited about the possibility. And we've been to a few events together, but we were at a Mariners game and just started talking about it. I think it just kind of naturally came up. I think maybe it was a conversation between you, me, and Garrett. Right.
We were talking about how fast a building could go up.
I think maybe in his slides there was some discussion of mass timber. And I think it just kind of naturally happened that we just started bouncing ideas off of each other. And a big point of what the grant work is going to be about, as kind of the background reason for it, let's say, is that mass timber technology, which I can talk more about, it's essentially always a hybrid system with other construction. And so that other construction has constraints and their own logic. Even if everything in the building structurally is big pieces of timber put together, they're still put together with something that has its own logic.
Right.
So
either a Simpson connection or some other pre-engineered connection that has to work together with the two systems, right? Or multiple systems even.
Absolutely. And what I think we're going to discover is that concrete masonry, as, let's say, primarily the lateral force resisting system, and it's going to do other things for us, but let's say the genesis of why we think it's worth looking into.
Right.
We think that the specific logic of how CMU can come together meshes really nicely with the way that the logic of mass timber works. There's nothing saying that certain construction logics have to work together. But if you zoom way out and go...
look at a 30,000 foot level.
Yeah. You say, what are we doing with these methods? We have put something together in a factory There's some version of standard sizing, although those are fungible to an extent.
Yep.
And they have specific technology that allows that to happen. You bring it to the site, and a lot of the work is done. You put it together with a smaller but very skilled crew. The description I just gave
is for both CMU and
it's agnostic
for CLT.
It's the same description.
Right.
You can't really say the same thing about any other system.
I think the only one that comes close would be steel.
Right. So descriptively it comes close, but when you zoom in on, let's say, the code level of what's required to get it to work, that's when steel has other requirements. Not even challenges, let's say. You just have to do certain things.
Yeah, they're just different.
Right. And what I think that we're, again, going to discover is that, it's kind of a boring point to make, but there's no one combination of systems that's going to work everywhere.
Right.
What we want to do is discover where CMU and CLT technology, mass timber in general, where they can come together. And at least in our initial study, we think that's going to be at the mid-rise, let's say 6 to 8 stories, multifamily projects with possibility for commercial uses, mixed uses at the ground level or throughout. And that's a pretty specific use case, but happens to be a ubiquitous one.
Right. It happens to be one of those things that helps, one, address the need for housing, for low-cost housing, too.
Correct.
And the need for building communities not just around housing. We don't want more and more sprawl, right?
Correct.
We want to go up a little bit more, get a little bit denser especially in our cities, but our sites are very constrained too. I guess going back, the title of your project is what?
We've been calling it wood/block.
Wood/block.
If you just look at it and say wood block, it gets at what we're trying to do is that you say these two things together.
Yeah.
We want CMU, and there's a certain terminology that you're going to be teaching me.
Right.
But let's just say concrete masonry in general.
Yeah.
We want that in the scales of buildings that we're talking about to become the first choice or the default assumption when you talk about projects like these from the beginning.
So really what we're trying to do is change these 5/2s to be 7, 8 stories of straight CMU CLT.
Yeah.
What does it do? The requirements that it changes is that, hey, instead of doing a type 5A over a type 1 construction, we switch over to a type 4C. Is that right?
Yeah. Let's talk about certain terminology and just aspects of how this all can line up. So in the International Building Code, there is, and part of this is going to be the deep dive into code research that we're going to do in this grant. But I believe it was in the 2009 edition of International Building Code when high-rise was put in as an official definition.
Okay.
It has been talked about in basically special requirements for certain building types for a long time.
Right.
But in 2009, high-rise
finally got added as a definition.
As a real definition. And in the model codes, what they mean is anything that is occupied above 75 feet from lowest fire access.
Okay.
So you're basically talking about the adjacent road.
Right.
How does a fire truck get within 75 vertical feet of where people are?
Yeah, and that's based on ladder heights.
Ladder heights.
For ladder trucks.
Just like
water stream availability.
It's like other constraints, right? Now that limit can be adopted as is. It can be modified. I think I have this right. In Massachusetts, there's kind of a different definition that talks about 70 feet that measures to a different place. In Washington, interestingly, if you have an occupied roof deck that is below 50 occupants, that is not considered an occupied floor. So this is how we can have certain roof decks. Yeah. It's interesting.
A rooftop bar that only has a maximum
occupancy of 45 people would not be considered.
Architects will be familiar with the 749 square foot.
Right.
Because that just puts you at 49.9.
Right. Yeah, exactly. Right.
And there's games that you can play to do
kind of
fun
plays
things
into
with that.
ADU as well with the 800 square foot ADUs, right?
Exactly. Right.
Okay.
So 75 feet.
Yeah.
It's useful for a number of reasons to not put yourself in high-rise territory.
Absolutely.
Basically, fire life safety requirements bump way up when you go into that territory.
Yeah, so you're looking at hundreds of thousands or millions of dollars in increased construction cost to meet the code requirements
and there are just
of a high rise.
Other systems that come along for the ride. For example, you need the secondary water tank. Elevators have different requirements. There's a bunch of stuff. It's not impossible. Happens all the time.
All the time, yeah.
But, and this isn't absolutely the case, but once you're in high-rise territory, it is beneficial to go high to get those costs to work.
Yeah,
right?
To get the cost per floor down.
There's a scale payback.
Yeah, exactly.
There. It's why it can be helpful to ride that 75 feet line.
Okay.
Let's talk about what a multifamily building looks like in
general.
Do that. You have a ground floor that is generally a little bit taller than all your other floors.
Makes sense.
And then you've got a bunch of other floors on top of that. Let's just call them 10 feet.
Sure.
It can be lower, but let's just use square numbers.
From finished floor to finished floor is going to be 10 feet.
Right. So if you have 15 feet at your ground floor, and then 10-foot floors above that, assuming, let's just say the site is totally flat.
Right.
You're going to be right at or around that 75 feet at your highest occupied floor.
Yeah.
Right.
At 8 stories or 7 stories, right?
Exactly. But then there is structure above that.
Right.
Right. Because your highest occupied floor, you have a roof and all the walls above it. Right. So you're at something like 85 feet. Right. So the question is, how do you get to 85 feet? The ways prior to the 2021 International Building Code revision, there were only a couple ways to get there. So let's talk about construction types.
Yeah, absolutely.
Type 1 and Type 2 are basically concrete and steel construction.
Non-combustible.
Non-combustible.
Right.
The difference between 1 and 2 doesn't matter so much. It's just kind of a fire protection level. You can get there with those construction types, meaning you can build in one construction type up to that level.
Right.
But there is an efficiency of scale that makes it beneficial to go higher.
Again, makes sense.
Exactly. So, okay, if we're not going to do that, then what about type 3? So type 3, it's a historically interesting type, non-combustible exterior walls.
Okay.
And then anything you want on the inside. So let's say combustible.
CMU box store.
So think of a brick exterior wall building with wood floors and wood interior construction. I don't have the numbers in front of me, but it doesn't matter. You can't really get to that 75-foot upper floor, 85-foot total building height. It's just not allowed in the code. There's a table that literally says,
it's just not permitted.
Here's how high you can go. And depending on the use, here's how many stories you can go.
Right.
We're going to skip over type 4 for a second because that's where we're going to end.
Yeah, we're going to end up there.
So let's go to type 5. So what is type 5? Type 5 is literally anything. Type 5 is anything that's allowed within the scope of this code.
Pretty much anything that has a division within the IBC.
Right.
And it fits within the requirements.
If it's got a listing, if it's capable of doing it.
Right.
That's what it means in principle. What it means in practice is light frame wood construction.
Right.
Now, you have fire ratings for other reasons, for occupancy separations and whatnot, but on its own, the requirements are quite low. But that has an even lower maximum height.
So like a 5A construction.
Right. I believe that is either 4 or 5 stories.
Right. It's probably 5 because we hear 5/2 quite a bit.
Right. The part that I'm forgetting is whether that's a Washington specific amendment. Okay. Either way, you can't get to that 85-foot height.
So if you're mixing types, you can have a non-combustible plus a combustible system. So this is
where this innovation, and it's an important historic innovation of the podium.
Right.
So what you do
5/2 or 6/2 or 7/2, whatever it is, or
whatever gets you to that maximum height. So you build as high as you can within either type 3 or type 5, and that is on top of a concrete podium.
Right.
So people will be familiar with this just driving around. You see a big concrete 1, 2, maybe 3 stories with wood construction on top of that. That's why. Right? That's an important innovation because that uppermost layer of concrete is literally separating building types.
Right. That's a 3-hour fire barrier.
Exactly.
It's really just separating fire zones. It's compartmentalization.
Exactly.
Right. And we teach that a lot in Masonry about compartmentalization. But typically what we're looking at is separating horizontally the spaces.
Yeah.
Not vertically or with a floor.
Yeah. Right.
CMU walls, not slabs.
Right. Again, that's what lets you get up to that height.
Okay.
Right. So now you can basically add as much concrete as you want to get up to whatever height limit. And if you're interested in staying under the high-rise definition, that's usually 1, 2, 3 stories of concrete with 4 to 5 stories of wood on top of it.
Okay.
The specific mix depends on the site and whatever, right? But there's a problem. You have to translate forces between building types.
So either increasing them or decreasing them based on the compatibility of the materials.
So the wood construction has a certain logic.
Right.
The concrete construction has a certain logic. And they have to meet up right at the uppermost concrete deck.
Right.
The architects listening will be familiar, if they've done CA, about how complicated that uppermost slab can be. 14 inches thick.
Yep.
Lots of embeds and sleeves and all kinds of shenanigans.
All of the pieces that you needed to connect.
Right.
It's really a foundation.
It really is.
For another building on top of it.
Correct. And you've put it up in the air. So you got to do things to make that be possible.
And it's not very easy to epoxy in new dowels or hold downs or anything like that, because a lot of times they're using post-tension to reduce the amount of rebar required or reduce the thickness of those slabs.
Correct. Again, the architects who have done CA will be familiar with, you get about 95% the way there.
Perfect.
And inevitably, there are things that have to be drilled in or cored or whatever, right? And now you're scanning, and you're making compromises, right? So I skipped over a type.
Right.
Type 4. Type 4, before 2021 International Building Code, I will fact check myself if I'm wrong on that, was essentially heavy timber.
Yeah, your mass timber, your glulam construction, your 6x6 or larger timbers.
So the specific definitions matter, and I don't remember what the minimum size is to like sort of tip into the heavy timber category. But in 2021, 3 new types were introduced.
Okay.
I could be wrong, but I think it's the biggest revision, the single biggest year over year or edition over edition revision. There are 4 types within type 4.
Okay.
So when you're talking about type 4 construction, you are generally talking about mass timber.
Okay.
So what's mass timber, right?
Right.
It is smaller pieces of wood put together into bigger pieces of wood.
Right.
So in general, the 3 most common elements are cross-laminated timber floors. CLT. So these are 3, 5, 7, 9 more plies thick that are cross-laminated, so oriented
they're laid
90 degrees.
Perpendicular to each other, similar to how plywood is made.
Right.
But instead of using laminated sheets, they're using 2x, essentially. And to tout CLT a little bit, I know I'm more masonry focused, but with the goal of reclaiming wood that is not necessarily good to use in most construction aspects.
Correct.
Right? Shop grade lumber.
Correct.
In those middle layers.
Correct. As
we were talking about a little bit earlier before the podcast starts. But we're talking about moment and shear demands.
Yeah.
Right? If we can put the good lumber on the outside, a little bit less good grade on the middle.
Correct. Matters more on the outside.
It matters a lot on the outside, not so much in the middle. So we can go into these forests that have been devastated by earthquakes or fires or tornadoes and reclaim the lumber that's been knocked down.
Or just the possibility of using the tree more efficiently.
Right. Yeah.
We can use pieces that would otherwise not be usable. If you have to cut something into a 2x6, let's say, that requires a certain size. Well, you don't have to use that exact
a 2x4 or a 2x3
or whatever millimeter size that the engineering requires.
Right.
So in 2021, 3 new types were added to the Type 4 designation.
Okay.
And then the sort of like historic one is, let's say, the 4th subtype, which is heavy timber, right?
Right.
So now you have 4 types. You have Type 4A, B, C, and HT, heavy timber. So what does that mean? It's kind of all based on fire testing.
Okay.
So if you're going to build a building with mass timber, I forgot to talk about the other 2 types.
Yeah, sure.
So you got CLT,
yep,
cross-laminated timber floors. Well, cross-laminated timber. It's generally used as floors. It can be used as walls, and we're going to talk about this when we talk about lateral systems. But it's generally used as floors. And then you've got glue lams.
Right, which we see all the time.
Which people will be more familiar with.
Yep. But
you can have a glue lam column or a beam, right? So this is a one-dimensional buildup.
Right.
You take board.
2 bys of whatever width you need.
Right.
And then they come in modular sizes. Mm-hmm. Every ply is 1.5 inches thick.
Yep.
And you just add however many you need.
Yeah.
And then they're glued with a resin and squished together, heated up a little bit to set it all, and then cured, and away we go.
Right. So now you have something that's acting not exactly monolithically.
And again, we can use the good lumber on the outside and the little bit worse lumber on the middle.
Right. But it's acting more monolithically than it would otherwise, right?
Right.
So you've got glue laminated columns and glue laminated beams.
Okay.
There are other things that you can do
because there's nail laminated plates as well, and
there's dowel laminated timber, which is an amazing technology that relies on a gradient difference in the water inside the wood, which is fascinating. There's lots of others,
right?
But if we sort of stay high level and think about what are the parts that are going together, you got floors, you got columns, you got beams,
right?
So you can sort of think of it like steel construction.
Yep.
So Type 4, you've got Type 4A, Type 4B, and Type 4C. Think of A as the most fire resistive of that category, of this sort of subcategory, and C as the least fire resistive of these categories.
Okay.
In the same way that construction types 1 to 3 to 5 is less fire resistant and therefore lower maximum height and size, analogously, within Type 4, Type 4A, you can build, I believe, 270 feet tall.
Wow.
Type 4B, I believe, is 180 feet.
I've heard that number.
And Type 4C is 85 feet.
Okay.
Type 4 heavy timber, I'd have to do my homework on.
Yeah, I think it was 65 feet is
you could
what
be right.
I've seen there.
Right. That's the sort of historic precedent.
It's existed for a while. Right. So here it is as a code option so that you can continue to build those buildings based on empirical data that's existed. Right.
So Type 4A, you have to basically enclose with drywall.
Okay.
You're not seeing any wood.
Which obviously we want to see the pretty timber when
it could in principle be just a good way to build.
Right.
And it lets you build very tall out of wood, but you're not going to see it. Right.
Right. And from an engineering mind perspective, it makes you worry about the creep in the building as well. Right.
Interesting.
Where
I hadn't thought of that.
You're up 270 feet as the building wood is creeping down.
Interesting.
That's a lot of deflection to worry about. Say if you have metal paneling on the outside and you don't give yourself enough expansion joints, or floor to floor height is going to shrink that 1/2 inch throughout the life of that building.
Interesting.
We've seen that with brick veneers quite often with the face brick. If we don't give ourselves that horizontal
joint every floor, every other floor, or whatever.
Once you get above 30 feet.
Yeah. It can start.
People are wanting 3/8 of an inch. And I'm like,
it's
well, we're gonna go with 1 inch on that one, or 3/4 of an inch, and at least to give us some kind of movement there. Otherwise, we're gonna start seeing brick cracking or metal panels buckling or things like that. So, 270 feet.
Yeah, it is a lot, and
it's only a few trees that go that big. So,
but I mean, exclusively out of redwoods. Let's set that aside for the moment because you might be remembering the 75-foot limit. If you're building 270 feet tall, you are no question in the high-rise territory.
Absolutely.
So let's talk about type 4B
and
then C. So B, I believe, is 180-foot limit.
Yep.
Still in the high-rise territory,
right.
No doubt. But the encapsulation requirements for the mass timber is lessened. And I could be fact-checked on this, but I don't believe that ceilings need to be encapsulated at all. I think there's other requirements.
Maybe the walls do, but not the ceiling. Maybe it's a fireproofing spray or something like that. Right?
I'll need to fact-check myself on that, but I believe that was a difference.
Right.
Now, you're still in the high-rise territory.
Still in high-rise, which if you're going to go in high-rise, again, economy and scale go higher.
Right.
So maybe it doesn't make sense for CLT to be in that atmosphere.
Right. And then there's type 4C. Type 4C has an 85-foot height limit.
Mid-rise.
Which becomes very interesting because if you have a 75-foot threshold to when you tip into high-rise territory, and then you have one floor of construction above that, you're at 85 feet.
Right.
Well, type 4C has an 85-foot height limit. It aligns nearly perfectly.
Right.
But there's another way that it aligns nearly perfectly.
How's that?
In the building code, there's also requirements, maximums, for how many stories of certain occupancies you can build.
Right.
So if you're talking about residential construction at this scale, you're talking about R2.
Right. So these are our group.
Yeah, it's multifamily.
Right.
It's not a hotel.
So this is like a group R2 building, right?
Yeah. So, just think apartments.
Right.
Right. That in type 4C has an 8-story limit.
Okay.
Makes sense. Again,
lines up
perfectly.
The 85 foot.
So we have 3 things lining up perfectly. 75-foot height limit for not being in high rise, 8 stories with typical floors and a little bit of squish for sites and floor to floor heights.
Right.
Puts you at 8 stories. And type 4C lets you build up to 85 feet without needing to have goofy things happen.
Right.
It turns out that it is, and this is part of what we're going to be investigating in the grant, but my initial code research has showed me that it's the only type that lines up in this way.
Oh, okay.
You can do it with type 1 and 2, but you could go higher.
Right.
You can't get there with 3 and 5. You have to build a podium.
Right.
This is the combination that lines up in this way.
So let's talk about that as well. So one, not only are we not mixing types.
Correct.
We're also not having to bring out different trades at different points and mess with all of that coordination and collaboration between the 2 different trades.
Correct.
Because PT slab people are totally different than your typical general contractor. They're very specialized.
Fundamentally different.
Right.
Yeah.
So then how does that marry up CLT and CMU?
Yeah.
Right.
So, and this is where I'm going to be getting an education from you in particular.
Yeah.
So before our meeting at the Mariners game, I don't think that I would have considered concrete masonry acting in a shear capacity.
Right.
I don't know if I would have had that in my head.
Right. But
it totally can.
So let's talk about the shape of these buildings. So the shape of these buildings are typically rectangular. Okay. They might have some ins and outs to them.
Right.
But you have a core that separates 2 different living sides of a building, if you will.
Right. So architects will be familiar with the term double loaded corridor.
There you go. Yeah.
That is
it's just efficient design.
It's an efficient way to do it. And it sort of keeps things at, let's say, manageable scales.
Right.
And also works well with most sites.
Correct. Right. But typically on either each end and in the middle or just on the ends, you'll have an elevator or stair core.
Correct.
Or both.
Definitely.
Right?
Yes. I will say unequivocally.
Well, you at least have the 2, right?
Correct.
You also might have a central core.
Correct.
Right?
You're definitely going to have 2, possibly 3.
Right. Depending on how long your building is and the amount of feet space between exits and everything, right? All the fire requirements.
Absolutely.
Now, typically architects would design that with a cast or specify, hey, I want a cast in place concrete core with wood shear walls.
Sure.
Right?
Right.
Or if we're mixing types, might as well put it up as concrete shear walls. Right?
Sure. So back to the podium type, what we often see is concrete shear walls for those cores up to your highest level of concrete.
Right.
You could go concrete above that, but just physics says that it needs to be less and less as you go up.
When you start mixing concrete shear walls with wood shear walls, the concrete's going to dictate the forces. So it doesn't make any sense to the wood structure.
And there's an interface issue because you have other wood shear walls.
Right.
So you just build the rest of your cores also out of wood.
Yeah.
But yes, so you have these sort of continuously vertical spots that generally happen in every building. I can't really think of an exception.
There's one in Spokane that I can remember when it was going up that we were looking at it. We're like, that is Swiss cheese. And it was one of those questionable designs from an engineering perspective. Sure. It's like, I don't like how they did that, but I could see how it could work, right? Sure. But typically we'll see stacked windows. We'll see stacked floors, floor to floor to floor. The units are pretty much the same. You might have an ABC of each unit that are kind of separated and differently.
So an efficient way to do it is across a single floor, you can mix a lot of types without a whole lot of headache. It's when things stack vertically that when things start to change, for a number of reasons, it's more efficient to have things stacked vertically.
Right.
You can imagine
from a mechanical standpoint, from
plumbing,
electrical supply, everything, right?
All of it. But structurally too.
For structurally, it makes a lot more sense to be straight vertical too. Right.
No transfers.
Right. Yeah.
Baked into the type, you've got a few categories of locations where something could be continuously vertical and not change length or width over the whole height of the building.
Which lends itself perfectly to CMU shear walls.
Exactly.
Right.
So when I was studying for the sort of code background on this, I looked into, a concrete masonry shear wall. That's a new thing for me. There are apparently 3 categories of how that reinforcing can work.
Yep. So you have ordinary, intermediate, and special.
Right.
And all of them depend from less ductile to most ductile requirements.
And one thing that we're going to get into is how seismic considerations overlay onto that. But as far as I can tell, if you use intermediate or special reinforcing, you can build up to, and in a lot of cases, quite exceed this magic 85-foot height that we're talking about. So what it convinced me of is that this is a possibility that isn't a huge stretch.
Right.
I can very easily imagine what the shape of these cores and walls that are CMU, that are acting as the lateral support for the entire building, what those look like. They don't seem crazy to me.
Right. It seems like
seems plausible and maybe even conservative. Right. Now, I can tell you that when you compare that to concrete construction and wood construction, very typically in the concrete base of a podium project, the size of the concrete wall is going to be determined by the amount of rebar that needs to go into it and the associated rules about what the concrete cover needs to be, right?
Yep. There's some ratios there that we have to always look at as well, right?
When you get to the wood levels, those change, but you're talking about
the hold down requirements,
the hold down requirements, double-sided shear walls, all this stuff. It can get complicated really quickly, and the engineers who are listening will be familiar with, shear wall tables and what all combinations of they're used to doing it. If I'm close to right about the case here, I think what we're going to find is that if we use concrete masonry, it might be kind of simple.
Right.
I don't know much at all about, let's say, what the reinforcing needs to be, let's say, in special. But I've read the code, and it's kind of a short section.
It is a very short section, but it's very simple. It just says, hey, we have a maximum spacing for our reinforcing.
Right.
There's a certain ratio of area of the wall that we have to have as much reinforcing minimally in there, right? We're going back to what we talked about earlier with ductile versus brittle failures. The whole point of a special reinforced masonry shear wall is to get and force
create
a ductile failure so we can see it failing.
Right.
And get everybody out first.
Right. And not have the wall blow up.
Yeah, exactly. Right. Unlike URM buildings where it is very catastrophic.
Right.
Right. So going back to your study, it's going to be marrying up CLT with CMU.
Yep.
Shear walls.
Yep.
Elevator cores to take the lateral forces.
Correct.
Bearing walls, we can look at either using CMU as our fire barriers between walls or still using light frame construction or heavy frame construction even, right?
Well, and one thing that we've been talking about is setting up a sliding scale.
Yeah, so we were talking about a 3-sided sliding scale where each vertex of a triangle is a material. So one is CMU, one is CLT, and one is light frame wood construction.
Right.
And in reality, we're going to have a mixture of all three.
Correct.
Right? Because you're not going to have all of the interior partitions be CMU.
Yeah.
It just doesn't make sense for a lot of people. Right?
Well, not only does it not make sense,
it's not allowed.
It's not allowed, and you're going to have that mix no matter what.
Right.
In every building type.
Right.
If you're in type 1 construction, you're not casting in place demising walls between units.
Exactly. Right.
So let's say it's not an extra step.
Right. At a certain point in the project, it goes from being mainly concrete focused to now it's light frame kind of focused. Right. And then with ours, we talked about CLT being mainly for floors because the walls tend to be a little too rigid. Yeah. Right.
Let's stay on the sliding scale for a moment. Yep. So on one vertex, you have mass timber. The other vertex, you've got concrete masonry. The other vertex, you've got light frame construction.
Yep.
If you have a totally equilateral triangle, then you're sort of in one balance between those.
Right.
It could be that depending on your seismic zone, for example, that you need more lateral support than you would in a lesser seismic zone.
Right. So you
would tip
point wherever in that. So my thought is that if you got a triangle, right,
and you kind of picture that on a graph.
Picture it on a graph, right? And you can put a point anywhere in that graph. Maybe it's 60% CLT construction with 10% light frame and 30% CMU, or wherever that area is.
The total is 100.
Right.
So if you increase one, you're going to decrease the other.
Absolutely.
So in a high seismic zone, you might need more concrete masonry for lateral support than you would otherwise. In the otherwise condition, those could be mass timber elements.
Right.
But in the higher seismic zone, you might need more CMU.
Right.
Right. So the optimal balance between those is going to be project-based, site-based, labor-based. There's lots that could go into it.
Parameters to look at.
But the lateral, meaning the CMU, is never zero.
Right.
Right? So let's zoom out again
Yep.
and then think about what this configuration looks like. So you've got CLT floors.
Okay.
You still have glue lam post and beams.
Right.
You're still using the mass timber for that. And what posts and beams do is act in gravity.
Right.
So where you require lateral force resistance for seismic or wind or some other live load case that I'm not thinking of, that's where you have concrete masonry.
Right.
And so there are stair cores.
Yep.
Elevator cores.
Corridor cores.
Corridor walls.
Exterior
walls.
Shells.
Unit demising walls.
Mm-hmm.
There's lots of places where things stack or can stack without penetrations that make this possible.
Right.
So if we then layer in this triangle graph that we're thinking of, there's some mix there between what's the right amount of mass timber and what's the right amount of concrete masonry. And then everything else is either light frame construction or some version of panelization.
Right.
So you can have a panelized exterior wall, you can have panelized interior walls, you can do all kinds of stuff, but they are not structural.
Right.
In the parlance of the building code, it's not the primary frame of the building.
Right.
Let's talk about primary frame for a second.
Sure.
In type 4C, the primary frame of the building, so what are we talking about? We're talking about how the damn thing stands up.
Right.
So gravity.
Yep.
And lateral.
Yep. Our two forces, one goes vertical, up and down.
Right.
Lateral is left to right.
Right.
North, south, east, west, right?
Right. In dynamics, there might be a third category that I'm not thinking of, but it's
your
still,
lateral is the dynamic movement, and your statics is the gravity.
So both of those together, that's your primary frame. And in Type 4C, that has to be 2-hour fire rated.
Okay. So in order to get a 2-hour fire rated CMU wall, we're looking at a non-grouted 8-inch wall, a non-grouted 6-inch wall.
Right.
Right. Yep. But we have to grout it anyways for reinforcing to get it to stand up.
Right. So it just naturally happens.
Just happens, right?
So, and this is a key difference. And what we might find is that it might be one of the determining differences between using other lateral force resisting systems versus CMU.
Sure.
So other lateral force resisting systems.
Like wood shear walls.
Wood shear walls.
Okay. A wood shear wall by itself, maybe half an hour without any JIP on it.
Right.
I don't even think it's
rated. It might not be rated at all.
Right. Because the plywood's not thick enough.
Right.
So to get a rating, there's an ASTM E1119 that we go up against a furnace with the wall. It's a 10 by 10 by whatever the wall assembly width is.
Right.
It goes up against the wall for however long it's trying to be tested for. And then they put a hose stream on it. And if it can stand with load, then it's given a fire rated.
Interesting.
For non-combustible materials, they get to go up against the furnace for half the time with a duplicate specimen if the first specimen fails.
Interesting.
And then the hose stream test.
Interesting.
So you take a CMU wall, an 8-inch CMU wall, you put it up against the furnace for 2 hours.
Yeah.
You bring it out, and I have a great video of this.
Oh, man.
It's awesome. You bring it out afterwards, and you spray it with a hose stream, and nothing happens.
Well, I was thinking to myself, what would happen? And I mean, I could imagine...
You might get a little bit
of
imagine
things
from
popping off a little bit.
But that's nothing.
But I think that's going to behave fundamentally differently than other things.
Yeah, if you look at a hose stream after a 2-hour fire-rated wall assembly being a light frame construction up against it, the hose stream goes through in 10 seconds.
Yeah, I mean...
Right, and then there goes the lateral ability for that wall.
The kind of shorthand that architects use, and this is kind of pulled from various UL listings.
Sure.
If you have a 1-hour rated wall, that's 1 layer of 5/8 Type X JIP on both sides.
Right.
Or the side you're trying to protect.
On the side that you're protecting,
right. If it's 2 hours, it's 2 layers.
Right, it's pretty simple math at that point.
But 2 layers of rock, I imagine, after being hot for a long time.
It doesn't take very long for a hose stream to go through.
It wouldn't take very much. Now, how's the wall performing?
Right.
Now you have
you don't have any lateral stability to it anymore.
Correct.
Right.
Yeah, right. So what's going to be interesting when we do the kind of grant study is to take a lot of factors into consideration. So one of the factors is what's the inherent behavior of the wall?
Absolutely.
If your lateral system were light frame construction, you've got 2 layers of rock and interesting detailing at the intersections that maintain the 2 hours.
Yeah, with a continuous floor sheathing across the barriers and everything.
And it might require some specific testing and interesting detailing. Well, okay, that has a certain cost and schedule implication. Right. You compare that to CMU.
It's just inherent with the material.
You can't not do it.
Right.
In fact, I think it might even be 3-hour rated.
If you go east, you get 4-hour rated.
Right.
Right.
And so we might just be in that territory no matter what. If the thing is acting in lateral support, and if that means intermediate or special reinforcing, and that just means solid grouting everywhere, then you're just there, right?
If you're looking at 2-hour rated,
right,
you get to Michigan and they don't have any seismic requirements. So you go 10 feet on center with your reinforcing each way, which is very efficient.
So I want to linger on that for a sec. 10 feet on center is...
It's almost unreinforced.
It's almost unreinforced. It's close to 2-way CLT column spacing.
Oh, okay.
It's much less reinforcing than a cast-in-place concrete wall.
Significantly less.
And I assume less, let's say, labor-intensive or just technically demanding than hold-downs with plywood nail patterns, let's say, right? Yeah. So I think what we're finding is that we're just sort of building a case for, oh man, if we shift a couple of assumptions then we could very easily use concrete masonry and not have to change much.
Right.
And by that, I mean, us as architects, we don't have to build in a lot of compromises that might otherwise be required with other systems.
Well, and there might be some drawbacks to it.
Sure.
Right? Maybe we do have a thicker wall assembly because we have to interior insulate the wall.
Well, I've been looking at this actually. A typical demising wall between two units is often governed not by structural concerns, but by acoustic concerns.
Oh, interesting. So you get the benefit of a masonry wall where
quite
sound transmission is not prevalent, right? Like,
so again, multifamily architects will be familiar with this, but you build essentially two furring walls back to back with separate plates.
Right.
When you take the total dimension of all that stuff,
you're at 12 inches or more.
You're at 10 to 12 inches, maybe more, depending on plumbing requirements that might need to go through it. It's kind of the same.
It's kind of the same, yeah.
Not to say that you wouldn't also have to do certain things at masonry walls.
Sure.
But they wouldn't necessarily have to be everywhere.
I think I'm thinking more on the exteriors.
Oh,
right?
Sure.
Where you have the exterior insulation requirements, but
sure.
In those locations, either we're doing integral insulation to bring down our U factor,
sure,
bring up our R value,
right?
Or we can even technically look at a whole building model,
right?
Yeah, and
I
really
can tell
benefit
you
from the mass.
When you're in the scale of buildings that we hope to implement this at, you might be there anyway.
You might want to.
You might want to, given current energy code requirements.
Right.
You might have to.
I think that's a benefit moving forward, actually.
Yeah.
So I have another program with Chekhov looking at the energy building requirements or building energy requirements and trying to educate architects and mechanical engineers on the benefits of thermal mass.
Right.
Modeling on a whole building scale rather than
piece by piece or layer by layer.
UA analysis, right?
Right.
Where maybe we've been pushed out because they're looking at
just because
individual
of the
elements
method of
rather
calculation.
than a whole building where your gym is such a small portion.
Yeah.
Right? Maybe switching your gym to CMU from a stud frame with steel frame interior, right? Your gym cost is like $200 a year.
Yeah.
Right. Oh, darn.
Yeah.
For that durability and maintenance requirements, right? But going back to yours, so that overall assembly doesn't really get that much wider, right?
Crucially, when we're doing initial studies, we wouldn't have to, let's say, overdo it on, oh my God, I have a CMU wall. That means it's 2 feet thick. No, it's not 2 feet thick. Right.
Well, and some people want to look at the architectural CMU aspect as well, right? Not only are you getting your exterior surface of your building we have a lot of textures and styles that we can add to the building.
Right.
You're not using CMU for everything, right? You're somewhere in that triangle.
Exactly.
And you're mixing these materials, and that was mainly for the lateral and the vertical aspects. Once you get on that outside of the building, now we're saying, hey, we've got these vertical sections that are CMU.
Right.
They're going to be exposed.
Right.
Okay, but in between them, you've got glass, you've got metal paneling, you've got wood paneling, whatever you want as an architect to get your style or your thought into your building, right? To make it unique.
Other ways to do lateral include mass timber panels, cast in place concrete walls, steel brace frames, or light frame
shear walls.
Any of those have the same constraints, or let's say analogous constraints to the triangle that we're talking about, in the sense that you're mixing systems.
Right.
If your lateral force resisting system is mass timber, it can't just be mass timber.
Right.
First of all, the height limit, I think, is 65 feet.
Okay. That's really short.
Doesn't get us to the height that we need.
Nope.
But also has hold downs. And kind of interesting connection detailing.
Almost proprietary. It's very engineered based. Right?
So, not to get too mathy, but mass timber on its own is very, very stiff.
Right.
Therefore, low R coefficient.
So high forces.
So high force, you don't get that divider.
Right.
So in order to get that divider, you have to use other steel systems, like I just said, hold downs,
BRBS,
various connections. Right.
Whatever. Yeah.
So you're talking about mixing systems anyway.
Yeah, right.
So then cast in place concrete walls. Okay. Again, mixing systems.
But cure times.
What really causes issues is getting the gears of the concrete logic to sync up with the gears of the mass timber construction.
Okay.
And what often happens is that you just do the concrete first.
And just ignore the CLT side or the mass timber side.
Right.
Altogether until the cores are all up, right? And cured for 28 days.
Right.
Right.
So two things happen. First of all, your concrete then has to be engineered to stand on its own.
Which sucks.
Just
for an 85-foot tall column.
Skinny thing,
or
right?
Even just with the walls,
right? With openings in it. Or walls, right? That's now just...
They're just blades
standing that out there in the wind. Trying to be fully cantilevered, right? Separate from that, there's a schedule thing.
Right.
Now, construction has started, but you haven't started your mass timber because you got to wait for all that concrete to finish. Okay. So now you go into steel brace frames. Okay. Well, those can be
pretty quick.
Those can be pretty quick. But remember that the whole thing has to be 2-hour rated.
Right.
Which means that there's encapsulation requirements or just very interesting detailing.
Yep.
Right. CMU, if I'm right about this, syncs up with the logic of mass timber construction at a sort of means and methods level,
right?
Where they're happening at the same time and they are almost literally leaning on each other to stand up.
Right.
And therefore gets a schedule benefit that, again, if I'm right about the case here, is just fundamentally unavailable with other methods.
Okay. It is a symbiotic relationship then.
Absolutely.
Right? Where
and this
we're going to build up 16 feet or 14 feet or whatever the height is with our first pour or our first lifts of CMU.
Yep.
Okay. No CLT on site yet.
Right.
Okay. We're just doing our shear walls. We're just doing our elevator course.
Yep.
While we're doing that, there's footings that have already been poured because they did all that before we came out with our CMU.
Right.
Okay. They're able to put their mass timber or heavy timber posts and glue lambs, getting ready for the planks to be brought out, right? The CLT. Then once we're up at that height, that's a week.
Yeah.
Right?
Yep.
The CLT comes out.
Yep.
We're doing our flat floor plates.
Yep.
We're bracing those walls now.
Correct.
And then we're going up higher now.
You're essentially starting over with
we're starting over again. Next story or two.
Let's sharpen it up even a little bit more. If you have a cast in place concrete core and that's your lateral force resistance system, you build that whole concrete thing first and you get those guys off site and now we're free to do all our mass timber. But we had to wait for all that to happen.
Right. A full 28 days.
Right.
Right.
If the site can allow for it and the crew is scaled properly, mass timber is about a floor a week.
Which is perfect.
So you go floor. But you had to wait for all that concrete to be in place. With CMU, also happens to be about a floor per week.
Right.
But they're happening at the same time.
Right.
There is CMU going in while mass timber is going in.
So instead of being stacked this way, we're stacked this way.
If you imagine the Gantt chart version of this, there's a lot of things that are stacked vertically.
Right.
Instead of horizontally with dependence.
Right.
Now, there are still dependencies.
Sure.
But they are overlapped in time.
Right. Like I can't build my next story of masonry without the bracing available.
Correct.
Well, if I'm finishing this first story. And then right after I finish that, you're putting the floor on the next day.
Now I'm not really waiting.
A day isn't enough to wait, right? It's okay. Darn, we had a 4-day work week this week.
Right.
Now we're going to spend a day cleaning and getting all the equipment ready for next week.
So that we can stay at pace, whatever.
At pace, right?
Yeah. We think that there's going to be savings or let's say efficiencies on multiple fronts.
Right.
So first of all, you're not switching construction types.
Yep.
Halfway through the project.
Right.
Right. You got the same crew the whole way. Second, you are maximizing this 75 feet limit.
Yep.
Again, in one type. Right. Third, we're going to do a bunch of cost analyses on material and labor and time. And we think that the combination of all those is going to come out ahead of other types. And crucial to that is pre-manufacturing, bringing things out ready to go, and having these schedules sync up.
With the skilled labor.
Correct.
For both.
Now, all of this requires, let's just say, management and staying on top of efficiencies that, let's say, haven't previously been aimed at.
Right.
But the reality is that construction seems to be the only industry that has gone down in efficiency since the 70s. It's totally amazing.
And it's kind of crazy that you think about that, because with AI and all of the other efficiencies in our typical workflow, construction schedules have wanted to be quicker and quicker.
Yes.
Right?
Well,
and the design side is getting squished.
Not only wanted to be quicker, but will only pencil if they can open at a certain time.
Right.
Holding everything constant. The site, the program, you're just talking about what is the mass of the building and how is it going up. If you don't have to compromise on much of anything else, and we save X weeks and you open X weeks sooner and that translates to X dollars, that can make all the difference in the world when margins are very small. Right? So we think that not only is it just an interesting thing to consider, it might just unlock latent possibilities. Right? There's lots of pro formas that don't work because can't open in time.
So it is one of those opportunities that maybe the masonry industry hasn't noticed.
Sure.
The architectural industry hasn't noticed.
Totally.
And so here we are coming together.
Right.
Architects, engineers.
Right.
Looking at the material that's been stealing market share from the masonry industry.
Right.
Even though I think that it's an opportunity.
Sure.
To work together. And so we're presenting that opportunity to work together.
Yeah.
And I think the cost of the study is not that bad either. So there's opportunities to work with the CLT industry as well.
Yeah.
There's opportunities to present at the Mass Timber Conference, right?
We want to very badly. And we think that when people see the numbers,
it's just going to make sense.
It's just going to make the case for it.
Right.
And again, it isn't going to work with every type.
Right.
But nothing works with every type.
But that's why we have multiple types.
This is why we have multiple types. This is why we have multiple construction systems.
Right.
It's noticing a gap and trying to fill that gap. But crucially, not with anything novel.
Right.
Everything that we will put together will be previously fully codified. Meaning, we're not going to even...
We're not changing the code at all.
Not changing the code.
It's just 2024 IBC or 21 IBC, whatever version we want to use, right?
Everything that we use is going to be fully codified.
Right.
And crucially, especially with the concrete masonry, everything's going to be a standard size and a standard...
Which is the whole point.
Reinforcing, meaning we don't have to invent anything.
Right.
We just have to put it together in the right way.
Right.
Right. So I think that it's a well worth it investment by the industry. One project that uses this
pays for it. Yeah.
Right.
I mean, when we're thinking about how big these buildings are, how many square foot per floor? We're talking 300 by 100 buildings or so, right? 300 by 100, that's 30,000 square feet.
Right.
Times per 8. Floor, times 8, 2.4 million square feet.
Yeah. Is there like a, let's say, conservative multiplier between square feet and how many blocks that translates into?
It does when we go linear feet of wall. If we're at 85 feet, we're looking at probably 65 square feet of block per foot of wall.
Right. One thing that would be an interesting study once we get into this is once we've sort of gotten our feet underneath us about, okay, generally, what is the minimum amount of CMU required just for the lateral? Now, you might want to use more than that for other reasons.
For demising walls or whatever, right?
But then we'll be able to do some math and say, here's the total square feet of the building. That on the low end is this many blocks, and in the high end is that many blocks.
Yeah.
Right? Without having to analyze every wall, let's say, it just puts you in a range. Yep. I mean, you could very quickly...
I'm assuming we're going to make models in Revit.
Oh, absolutely.
So we could just do a QTO.
Absolutely.
Very quickly.
And by the way, our structural engineer...
It's also in Revit?
Also in Revit. Sweet. Very, very competent. National, international.
Okay.
Doing projects in the US and in Canada. In fact, working on a CLT and CMU building currently.
Perfect.
So we're going to use that knowledge. I think we'll be able to get some interesting numbers really quickly. And actually, Washington State has something called the Washington Mass Timber Accelerator.
Okay.
It's basically an agency looking at like policy initiatives to introduce this stuff or use it more. I'm on the housing committee of that. This is what we're talking about.
Right.
How do you get it to those uses? And we think that it requires some out-of-the-box thinking.
But is it really out of the box? Think about it this way.
Yeah.
The number of URM buildings that are downtown that also have heavy timber cores.
Yeah.
Or interior.
Sure.
Right? What are their uses?
Yeah.
They already are multifamily.
Right.
This is not really a new concept.
No.
It is at our core what masonry is about. It's about those exterior walls. It's about the structural capacity and resilient and durable design of masonry.
Right.
To support residences and maybe CLT or light frame or whatever interior construction it is out there.
Like I said, we think we're going to discover a lot of alignments.
Absolutely.
And one beautiful thing with designing buildings is that at a certain point, the logic of the system can kind of just do things on its own.
Yeah.
And we think that the logic of mass timber and CMU and multifamily housing, the gears of those just kind of mesh up in ways that we're not going to have to force a lot.
Right.
It's just kind of fall into place, we think. And therefore just becomes instantly applicable. And like I said, a big part of that is that there's no code alternates here.
It's already predefined in the code.
It's fully codified.
Yeah.
It's available for adoption. Washington State has adopted it. Many other jurisdictions have or are in the process of adopting it nationwide.
Right.
And crucially, as far as the concrete masonry industry is concerned, you can get mass timber anywhere in the country from multiple sources.
Right.
Domestically.
Right. Same with block, right? The stat for block is there is a block manufacturing plant within 250 miles of every major metropolitan area.
Yeah.
The only outlier is Montana because there's a bunch of plains that literally nobody lives in. But
correct.
I wouldn't consider anywhere in that area of Montana major metropolitan.
But I mean, and this is, sort of baked into our grant proposal, is that we're looking at 6 cities. And by the way, if the exact choice of cities is not the right one, we can adjust them.
Yeah.
This is our first stab at it. They happen to be in all of the CMC regions, right? And representative of the full spectrum of seismic design.
And wind designs.
Exactly. So we've got it. We're hitting everything that we think we need to hit.
Right. And really, I think the whole goal of this is to be a basis of design for architects and engineers to understand that these two systems marry up very well and are worth considering on their next multifamily project.
Yeah. If you're a developer, if you're an architect, if you're an engineer, and you are working on a project like this, if you're considering a project like this, we want you to be able to take the final product of the grant, which will be, basically, it's going to be a downloadable thing. It's going to have
basis details, typical details that are going to be needing to
be
designed or engineered, but
it gets you a certain percentage of the way down the road.
Right.
Again, this is a boring point. Every project is going to have specific criteria.
Right.
We know this.
Right.
But this gets you on the right track. And even before then, it lets you know that it's possible.
Absolutely.
Right. So we think that the concrete masonry industry is benefited by reaching into new project types that, frankly, haven't been considered by architects.
Right.
It's also an opportunity for the mass timber industry because, again, they have to combine with usually another material for lots of reasons. Why not use one that syncs up nicely with it?
And to that point as well, where both materials are being very carbon conscious.
Yes.
And reducing the global warming potential of our material production procedures.
So trees are just
they're a storage.
Yeah, it literally makes mass by combining sunlight and carbon.
Right.
It's what it does. And it gives us air to breathe.
And then on the CMU side, even though we off-put some gas or CO2 when we're making the cement clinker,
right,
we absorb 43% of that over the life cycle of a CMU, and it sequesters permanently that carbon.
just creates it in the block.
It creates limestone in the block.
Right. Which is kind of an amazing story that I need to read more about to fully understand. But I mean, I can tell you it's just not well known because I've mentioned this to people and they don't believe me.
Right.
And I want to read more about it to believe it because it sounds amazing.
It's hard to explain when it's such a new technology that we're just understanding how to quantify it. Right. So I really hope this project gets approved.
Yeah.
If it doesn't get approved in Iraq, I'm going to be really mad. Mainly because it's not that much, right? Sure. It is one of those projects that has such a quantifiably measurable impact.
And this is, guidance that you guys have helped us with, is that if we're able to draw on the resources of all 5 regions,
it's not a big ask.
Well, and
$25,000 from each region.
And it benefits anyone, right? So we had initially considered, okay, start small and go national, but the starting small, I mean, there's just
again, efficiency of scale.
Efficiency of scale, exactly what we're talking about. If we can pool resources, and we think that once we've designed for the most constrained case, that the lesser constrained cases will have 50% of the work done for it already. That might even be conservative, and we might be able to scale back even more. Who knows?
Right.
But again, it's a basis of design. It gets you on the right track, and we think that both industries are going to benefit from it, which again is why we want to present at the 2027 International Mass Timber Convention in Portland. I've personally gone 3 years in a row. It's bigger and bigger every time. There are big names there, and deals get done there.
And in 2027, the NAMC, the North American Masonry Conference, is also held in the U.S. So we'll have you give a presentation there.
Awesome.
So that'll be really helpful as well.
Yeah. I've done some research just to boot up from nothing, right? But I have to hedge a lot at the moment because, well, we haven't done the studies.
Well, and we don't know how far out we need to push the schedule. And
I don't know what the
right
percentages is to give to stuff, but again, my instinct is to start conservative. And when I start conservative and I am confident that it's going to work, that just gives me confidence that we're going to end up in a good place with it.
I'm really looking forward to this program because, one, it has quantifiable goals. It's easy to see the switch from maybe a cast in place or a steel frame or some other project type to this new project type, so we can quantifiably gather data on how this project has impacted market share.
Right. We're going to get cost and schedule and local cost and schedule information
for each of the cities.
For each of our cities, we have an amazing builder on board to help us with this, BN Builders. They work nationally. Yep. They are a major employer in Washington State specifically, and we've worked with them on multiple projects.
Absolutely.
This team that we have, us and structural and contracting, this is not our first go-around together. It's not even our first grant go-around together.
Right. So let's just go forward, right?
Yeah.
It's not like this is a pilot project.
Yeah. When I was getting the team together, I didn't have to
think about it.
I didn't have to think too hard about it,
Well, I look forward to it. One of the cool things is that I'm going to give you a copy of this as well to submit with your grant.
Awesome.
It might shock people how long it is, but that's okay. We covered a lot, right? Yeah. So, and if anybody has questions more about the grant or more about how we can marry these materials up, I mean, you're going to be a good resource. I'm going to be a great resource.
Yeah.
The structural team is going to be a great resource. This BN Builders is going to be a great resource.
Yeah.
And the deliverables is going to be one of those things where here is the supporting documentation. Here's the basis of design that you need.
Yeah.
To be able to go and run with your own ideas of how you want to use this type of project.
Yeah.
And I look forward to that.
Yeah.
So thank you for coming on.
Thank you for having me.
This was amazing.
Yeah.
And I appreciate having you. Again, Alex Watchman from Clark Barnes Architects.
Well, that's a wrap on today's episode of In the Mix, where we put masonry in the spotlight, block by block, brick by brick. A big thanks to our guest, Alex Watchman, for sharing their time and insight with us. If you enjoyed this episode, do us a favor, click that follow button, leave a quick review, and share it with someone who cares about building smarter and stronger. You can connect with me, Adam Hutchinson, on LinkedIn, and find bonus content from today's episode at masonrymix.com. In the Mix is produced by Espresso Podcasts and hosted by yours truly, Adam Hutchinson. You can find the podcast wherever podcasts are found. Hosting of the podcast is made possible by the Northwest Masonry Institute. Thanks for listening, and as always, stay curious, stay connected, and keep building strong. See you right here next week in the mix.